Hey y'all. So we have learned about rate laws, and we've learned about how to use data to determine the rate laws, and specifically the order of each reactant with respect to the reaction. But couldn't it be easier? Shouldn't it be easier? Shouldn't we be able to just use the stoichiometry of a reaction in order to figure out the order with which that reactant is with respect to the reaction? Well, not necessarily. Let's take a look at this. Now, you can see that in the first reaction, ammonium and nitrite are both 1-to-1, and in the rate law, they're both first order with respect to the reaction. Perfect. In the second one, the nitrogen monoxide has a coefficient of 2, and the chlorine has a coefficient of 1, and the nitrogen monoxide is second order with respect to the reaction, and the chlorine's first order. Great, okay, 2 for 2. But wait, see, in the third reaction, now all of a sudden, take a look at the hydroxide. Hydroxide has a coefficient of 2 in the balanced reaction equation, but in the rate law, it's only 1. First order with respect to the reaction. That doesn't match anymore. And in the last one, holy smokes, the bromide ion, coefficient of 5, but it's only first order with respect to the reaction, and the hydrogen ion is a coefficient of 6, and it's only second order. Oh no, okay. There's got to be something else going on. There's got to be more to this situation. That thing, which I'm referring to, is going to be what we talk about today. Mechanisms. Rate laws are not determined by the stoichiometry of a chemical reaction. And the reason for this is because most chemical reactions do not necessarily happen in one step. Instead, they happen as a series of elementary steps that add together in series to give you the overall balanced equation. This is a lot like Hess's law. We learned about Hess's law in thermochemistry. We're now going to look at a Hess's law type situation here in kinetics. What we do in kinetics is propose a mechanism and then test its validity. In this next series of videos, this is what we're going to be looking at. We're going to be looking at reaction mechanisms, using reaction mechanisms, predicting reaction mechanisms, and then validating reaction mechanisms. But in the end, the most important thing to understand is that we cannot use the stoichiometry to predict the order with which each reactant is with respect to the reaction. We must and can only use data, experimental data, like we've looked at in the past, either graphically over time or looking at initial rates compared to initial concentration. So what do I mean by mechanism? Well, think of it like driving from one location to another. You don't just go in a straight line. You're going to make turns. You're going to have to start. You're going to have to stop. Some roads you could go faster, others you have to go slower. And so a reaction mechanism is much like that. It could be multiple steps, and each step, each elementary step, is essentially one part of the process. Now, we can think of this in collision theory as each elementary step is the most fundamental collision that can occur between two molecules, or in some cases, the decomposition of one molecule. In this unit, we are going to look at what is making a reaction mechanism likely, unlikely, valid, or invalid. And so that's kind of our objective. But understanding that each elementary step is comprised of simply a collision or a process, a fundamental process of chemical reaction, is the key. So let's define a few things with mechanisms. First thing we're going to look at is the fact that mechanisms are comprised of multiple steps. Now, each step, each elementary step, represents breaking and formation of bonds of different reactants or products. but not every single thing that shows up in a mechanism might show up in your balanced chemical expression. So if I look at a chemical equation, but then I look at the mechanism, if there are things in the mechanism that don't exist in the actual balanced equation, that's not necessarily a problem. In fact, it's fairly common. So there's two in particular that I want to focus on. The first one would be a chemical compound or a chemical which is formed in one step and then used in a later step. So any chemical that is formed in one step of the mechanism but then used in another step of the mechanism is called an intermediate. Okay? So intermediates are chemicals formed in one step, used in another. So they don't show up in the overall equation. We're going to talk about why in a bit, but the understanding here is that they'll essentially cancel each other out. So you never really see them in the balanced expressions. They're not a reactant, they're not a product, they're an intermediate. The other one that you won't necessarily see in a balanced equation are catalysts. Catalysts and mechanisms will appear at the beginning and at the end, but oftentimes will be utilized somewhere in the middle. Okay? So you'll often see them as a reactant in one step and a product of another step, but the process itself, they are not going to be appearing in the overall chemical equation. So intermediates and catalysts, two things which might show up in mechanisms but do not appear in the overall balanced reaction equation. The other thing about mechanisms that you're going to see is slow or fast. Slow or fast. Now that seems like a very binary thing, and to some extent it is. The reality is, in a mechanism, there's one step which is the slowest. Okay? That's what we call the rate limiting or rate determining step. We'll talk about that a little bit later. But the one slowest step will be ascribed the slow title, and all other steps will be ascribed a fast title. You can kind of think of this like you and a friend being chased by a bear, okay? It actually doesn't matter how fast you are, you just have to be faster, okay? Even if you're slow, as long as your friend's slower, you'll be fine. And in chemical reactions, the fast step might not be all that fast. It's just simply faster than the rate limiting, rate determining step, okay? So you're going to see the binary of slow and fast, but just understand that fast is not all the same, and neither is slow. All right, they don't always mean the same thing. They certainly don't mean the same rate, but we utilize them in these mechanisms to describe which step in particular is the rate determining step. Sometimes that step will be first. Other times it won't be. We're going to look at situations in this unit where both are happening, where the rate determining step is the first step or the rate determining step is a subsequent later step. Let's talk about the slow step versus fast steps for a second. Why would a step be slower? Well, in general, probability drives reactions. So a step which is slower is simply a step which is less likely to happen. And a step which is less likely to happen is less likely to happen either because the orientation of the molecules is more challenging, more difficult to achieve, or the kinetic energy of the collision is higher to achieve. Well, that's activation energy. So in general, we say that the slowest step of the reaction is going to have the greatest activation energy. And so we can actually utilize the potential energy curves that we've looked at in the past to look at mechanisms in a new way. Each mechanism represents a different opportunity for a curve. So a two-step mechanism would have two peaks, two transition states on the curve. Each transition state has a different activation energy, the energy with which those molecules would need to collide to achieve the energy of the transition state and thereby overcome it and move past it. The higher that energy is, the less likely that event is going to be to occur. So the event which has the greatest activation energy will represent the slowest step of the mechanism. So that wraps up today's video. Today, I introduced the concept of reaction mechanisms. Reaction mechanisms are the reason that we can't use the stoichiometry of a balanced chemical equation to predict the rate law of a chemical reaction. Okay? We're going to learn how to use mechanisms to predict the rate law in a future video. Now, a mechanism is made up of multiple elementary steps where bonds are breaking or forming. And in mechanisms, we can have both intermediates, chemicals that are formed at one step and used in a subsequent step, or catalysts, which are used in one step and then reformed in a later step. And there is a rate limiting or rate determining step, which is the slow step. All other steps would be considered fast in comparison. When we're walking away from understanding mechanisms, we are going to learn a lot more about how chemical kinetics actually occur. But everything comes back to our collision theory that we started this unit with. So I hope you enjoyed this video, and I'll see you in the next one.